That's
Yeah,
cannibalism.
that's cannibalism. It's eating your own species.
And
So
that happens
definition?
frequently.
Mm-hmm.
Okay.
Cannibalism is actually really common. Except with humans.
And now he's recording.
I am recording.
Well, can code cannibalize itself?
Jesse, you're the one who picks up on mine.
All right, so
Just
yeah, you're
haven't
closest.
deleted source code.
Do it. You have hardware that eats itself. It's good.
We were just talking about recursion.
Yeah.
So it recursively changes its own source code?
Yep. All right, so you got your window with pixels on it that you're painting different colors to draw your objects, right? So in a first version of this, we would have a memory that records the color of each pixel, and you store your memory in some order, and you say this is red, and this is blue, and this is green, and this is blue, and so on, right? But that's not how most systems are set up. In reality, most systems are set up with a color table which says color 1 is red, color 2 is blue, color 3 is green, and this would be a 1, a 2, a 3, a 3, a 2, and so on. So what can we do with this? Let's set color 4 to be black. And when you paint your pixels, you're not actually painting a color, you're painting an index in this color table. So we might paint our pixels like this, and each of these pixels has a 1 on it, and as the display is being refreshed, it sees a 1 in the memory here. It goes to the lookup table and says 1 is red, and so it paints that red. And it comes over here and it sees that these are 4s, and so it paints those black. And then maybe over here it paints these in color 5, which are also black. And this is black everywhere else. So what does this look like when you, yes, Minesweeper. What does this look like when this gets painted on the screen? The 1s are red, so you have a little red square up here. The 4s are black, the 5s are black. So we just see a red square in the corner. Now if I wanted to move that square somewhere else, I have 2 options. One, I can erase this by painting it black, and then I can draw it down here. That's the direct way to do it, but if this is something complex with thousands or millions of pixels to it, that's going to take a while, and we're going to see flickering and so on. Here's what I can do. I can edit my color table, and I can say 5 is red, and 1 is black. And now, what does my display look like? This is all black, so this goes away. The 4s are still black, but the 5s are red. Suddenly, my square moves down over to here. And it took 2 write operations. Change that to black, change that to red. So this is sometimes called video lookup table animation. And it's a way to give the appearance of things changing rapidly on the screen, but in fact they're both there, but we're using the color table to make one visible or to make the other visible. And it's a way to do really rapid, sort of low-grade animations. And it lets you do this painting during the refresh interval, right? And it lets you take advantage of XORs, because if we have things that are crossing, we'll get a different value where those 2 pixels overlap, right, if we're XORing, and we can set up the XORs to be whatever color we want. As opposed to if we paint this and then we paint another rectangle that covers it, and that second rectangle is black, we're going to have a little gap in that first rectangle, right? So we can use XORing to to mask that effect. So that's just, it's one of those things that when I learned about it, it became the thing I did for like the next few months. Because it just kind of opens up a lot of doors. So if you find yourself in a place where you want to do some animation, think about color table based animations, and it's a really powerful, really simple little trick. It's also called double buffering sometimes, right? You have a picture here of your first frame, you draw your second frame but in a color that's not visible. Might take you a long time to draw it, but you don't see any of that drawing because it's being drawn in the background color. But once it's there on the screen, then you go ahead, update the color table, first image disappears, second image appears. And if it takes a 1/15 of a second to draw that, which is a long time, right, your refresh rate will probably handle that okay, as opposed to slowly seeing the first image disappear and the second one appear, right? So that's just something to keep in mind. All right, let's talk about some built-in classes. So we know how to make linked lists, we know how to make trees, we know how to make hashes and stacks and queues and all these other things. But these things are all available for us inside Java. So let's look at the linked list class. So linked list is an implementation of a linked list, okay? And remember what we said about abstract data types. We don't really necessarily know how the linked list is being implemented. And there's lots of ways to make linked list: dynamic memory, arrays, magic dust, whatever. So generally we construct this with just linked list, okay? And it has a handful of methods available to us. Most importantly, add, which lets us add an element to the list. Get, which lets us retrieve an element by an index, so we can treat this as an array. Index of lets us find an object. Remove lets us remove an object if it's present, and
So if you have push and pop, you can treat that linked list like an actual stack.
you can treat it like a stack, yeah.
Can you treat it like a queue?
Yes, because we can remove the first element.
Oh, remove last.
But you don't get to choose what kind of data goes in each node. It's only, is it one integer or?
So this is where we get into generics. Okay, so if you look at the discussion of this, it's linked list, angle bracket, E. And some of these talk about strings or integers or doubles. So E is a generic type, okay? The type of elements held in this collection. And the description of the class is linked list, angle bracket, and this mysterious E. So let's make a linked list.
And you can make a linked list of linked list using this?
You can make a linked list of anything, including linked lists. So we'll make our main method. So this is how we would normally construct an object. We'll go ahead and import it. But it's going to warn us about this, bless you. It's going to tell us that this is a generic. Okay, linked list is a raw type. References generic type, linked list, angle bracket, E should be parameterized. So here's the deal. When you construct this, we say linked list, angle bracket, and then we put in the name of a class, which is the type of objects we're going to store in this. So we could say linked list string, LL, equals new linked list, angle bracket string. And that'll construct for us.
So what if you wanted to hold a string and an integer within the same node of a linked list?
Then you make a class that has an integer piece and a string piece, and you use that as the type of the linked list. Right, and once you can do that, there's no limit. Right, so this is another way in which this whole object mindset is really powerful. Right, because you don't have to hope that they give you a way to have 3 different types of objects in there. You just make a new type of class that's exactly the types of pieces of information you want, and now you say a linked list of laws.
So you'd still need to write a class per word node, and then the pass it would be linked list word node.
Yeah, so you'd make your word node, and it would be a linked list angle bracket word node. And the word node would have a word and
Just a list.
linked list of integers. Right, so it would have those 2 pieces. And so it wouldn't be a full word node, right? It wouldn't have the pointer to another word node. It's just the data part of it, basically.
Is there a print method?
Well, we're going to see that soon. So we'll add some things to our linked list. And we'll believe that those are in there. Now, linked lists, you can treat them like arrays, right? So we can say size and find out how many things we have in this list. And then we can say get, and we can index with an integer. So we can treat this like it's just a big array that hopefully is more efficient than a bare array. We can also say toArray and change it into an array if we want. So let's do the easy way first. Alright, so we'll go from 0 up to linked list size minus 1, and we'll just use the get method to get that element out of our list. So we're adding hello fun cool by, and let's see what we get out of this. Hello fun cool by. So it appears that it is adding things at the tail of the list, which is kind of cool. But there's another way to pull information out, which is to use an iterator. So we can use this list iterator method, and we pass it a starting location, which will be 0 if we want to iterate over all the elements in the list. And it gives us back an object of type list iterator, so it's going to be list iterator string. And a list iterator comes with a has next and a next method, just like scanners and just like other things that we're going to work with this week and next. So let's use this. So here's a different way to retrieve elements from the list. Is listed right there. It typoed.
That's the lowercase list.
Yeah. And this needs to be imported. All right, so now we've got a list iterator.
You can just right click on it to import the correct.
Yeah. You never have to work with Eclipse, except when it doesn't work. So there's a cleaner way to do this. Make a list iterator, and now every time that we say has next, it'll tell us if there's another thing in our collection, our list, that we haven't seen yet. And if there is, then list iterator.next will give us that next element. And when we run out of elements, it will come back with has next equals false, and then we'll exit. So there's another way to get you your data. And this is going to be useful when we're doing things like trees or hashes or things like that, where we don't have a way to sort of naturally index them with sequential integers. With a linked list, right, we can do elements 0, 1, 2, 3, and so on. So we have that option. All right, so that's a linked list, and it does all the things that you would hope you could do with a linked list and a whole lot more. You can clear the whole list by calling clear. You can retrieve the first element. Oh yeah, so most things you can clone, right? And it creates a new copy of your object. So if we have this linked list, and we construct an L1 list and we add some things to it and so on and so forth, then at some point we say L2 equals L1, right? This is setting L2 to be the same object as L1. It's copying that ID of L1 into L2, and now if I say L2.clear, L1 is cleared also, okay? So if you want a copy of it, this is not the way to do it. So you could say L2 equals L1.clone, and it makes a new list and it copies everything that was in L1 and puts it into L2. And now I could do L2.clear and L1 is still intact, right? Or I could make some change to L2 that made sense and L1 would still be intact. So it actually gives you another copy of it. But there's a critical word in here on clone, returns a shallow copy of this linked list. So shallow versus deep copies is another one of these potentially really confusing, but hopefully not concepts. When you copy an object, right? So this L2 equals L1 is not copying the object, it's just making a new reference to the object. A shallow copy is basically you've got a linked list. Okay, if these are strings, I'm going to get a new linked list, and it's going to have the same strings. But if this is something more complex, if this is a rectangle, so I have a linked list of rectangles, and I do a shallow copy, I get a new linked list, but this rectangle is exactly the same rectangle as this. And in the second node, this rectangle would be exactly the same rectangle as this. Now, it's a copy in the sense that on this copy of the list, I could delete this node. And in my original list, I still have 3 nodes. In my new list, I have 2 nodes, and this pointer is just hopping over. But it's not a deep copy in the sense that I don't have a new version of my rectangle here. This rectangle and this rectangle are the same. So if I do something like change the dimensions on this rectangle, the dimensions of this rectangle also change. So it's a copy of the linked list, but the data in the linked list is really just another reference to the same thing. If you really want a complete separate copy where you have your own list and your own rectangles and your own everything else, you need to do some kind of deep copy. And usually you're going to write deep copy routines yourself because you know what the pieces are that need to be cloned, as opposed to just using another pointer to the same thing. So it can be tricky sometimes when you're trying to make a copy of a more complex object. Sometimes you're getting a shallow copy and you don't realize it, and that can come back to haunt you. Yeah.
So in the case of a custom deep copy of your example, you would do like your first shallow clone, and then you probably have to like loop through and do this like I assume like rectangle would have a clone.
Yeah, so you could make a clone of rectangle and store that here, and then make a clone of this rectangle and store it there, and so on. And clone should be one of the few methods you get in the object class, right? So you can always clone, see if two things are equal, and a few other things.
Wait, that's an exact copy though.
Yes. Copy. Yeah. But the question is, when you say exact copy, what does that mean?
It can be identical to the first one. You can change the second without changing the first.
So you make an exact copy of this house, right next to it. Well, so you're building a new building. You're using new bricks. You're using new cement, right, and so on. You've got this new building. But what about the cat that was inside that house? Did you make a new version of the cat, or do you just have something which says Fluffy, right? And they both refer to the same cat. So a shallow copy, you'll get a new house, but the references will be to the same things the old house was referring to. Right? A deep copy, you'd actually create a new version of Fluffy, and now you have a totally separate cat.
So is this a deep copy then? This
You
clone?
can cut this one.
Clone is a shallow copy.
Okay. So always is.
Yeah, I don't know if there's built-in deep copies, because I think it's somewhat dependent on the nature of your class, right? And it's not binary. You might want to make exact copies of these things, but just copy references on these things.
Okay.
All right, so that's a linked list, right? And as an abstract data type, we don't know how it's being implemented under the hood. We know that we can push and we can pop and we can remove the head and we can add to the head and we can search for things and we can do iterators and all that kind of stuff. And we could write code in C to do that, whether we're using dynamic memory or we're using an array or we're using something different, right? We could be sending messages to someone who's just storing this stuff on a whiteboard, and every time you do a fetch it says, hey, give me item 7, and they type in what item 7 is, right? There's lots of ways to implement this. And nothing in here really tells you how it's being implemented under the hood.
If you want your linked list to store in front of it instead of at the tail end, or you wanted to keep it alphabetized, would you do something that extends linked list? Or
So you could do extensions, but you can also
peak last?
yeah, peak last will show you what's at the end, but not remove it. But you can add, So you can add first to put into the beginning of the list,
Oh,
right? Or you can add in an index. So if you want to keep something alphabetized, right, this is not the right class to use. You're going to be better off with something called a Treemap, which is built on the idea of a tree, so a binary search tree, so it'll alphabetize. So that's linked list. There's also array list. And array lists look remarkably similar. All right, you can add, you can clear, you can clone, you can for each, you can get an index, you can get a list iterator, you can remove, and so on and so forth. But they have different implementations. So linked lists are doubly linked.
They must have a parallel like index array going with it to tell you location.
Yeah, there's a lot of other side structures that are making these things work efficiently. So linked lists are doubly linked inside, which doesn't affect the user experience directly, right? It affects the performance, but we don't actually deal with the links themselves. So this is very fast for add and delete. Array lists are very fast for reading, and not as fast for add and delete. So, and that's usually seems to be the biggest difference between linked list and array list, but you can find all this stuff in Stack Overflow debates and stuff. But I found one with some pretty good orders of complexity. So this was a good one. So get index order n for linked list, order 1 for array list, right? Add order 1, but order n worst case. Adding with an index, order n for linked list, order n for array list. Yeah, so array list, main thing is access. But then for linked lists, removing is order 1. So depending on what you're doing, are you primarily storing information that's going to be retrieved later? Or are you building a set of data once and then you're just going to spend the rest of your time pulling data out of that, right? Or is it a mix? So that can kind of influence your decision. But there's lots of ways to do linked lists, right? In Java, there's linked lists, there's array lists, there's other versions of those. You can write your own, of course. And like everything, an array list is really an extension of an abstract list, which is an abstract collection, which is an object.
Can you go back to that? Because it looked like...
Back to this?
Yeah.
Yeah.
It looked like, yeah, remove and iterator remove are different on linked lists.
Mm-hmm.
What's iterator dot remove?
I don't know. It might be when you use an iterator to get an element, but each element that you get gets taken out of the list. So instead of removing with an arbitrary index, it removes them in some internal order,
Which
while
is
also
faster.
giving it to you,
Which
which would be faster. Yeah.
Bless you.
Bless you. All right, so so important themes here, right? Iterators, first of all. We're going to use iterators for hashes and for lots of other structures. There's a more general version of all of this, which is called a collection. Okay, there's also things called sets that are just repositories of objects, right? And if you just have a repository of objects, how do you pull elements out of that? You can't really say, give me element 1, element 2, unless there's some inherent numbering to them. So typically we use an iterator. Okay, and hashes are the classic place where this shows up. Because with hashes, you're storing data based on keys, and those keys generally aren't integers, or at least not sequential integers. They might be strings, they might be binary files, they could be anything. Right, so we use an iterator which says, give us our data back one at a time in some non-guaranteed order. And that's a common motif. And it's the same thing you're doing with scanners, for example, when you do input with has next and next. So iterators are a theme we'll talk about a lot. Thread safety is another theme. Most of these classes are not thread safe. Okay, so if you create a linked list in one thread and you start storing information in it, and another thread starts trying to store information in the same list, you might corrupt your list. Okay, and it's pretty easy if you think about C code or bare bones Java code for doing list insertions. what do? You follow these pointers down, and when you get to some point, you change this previous pointer to point to the new node and change this to point to the old next node. And if you do that from 2 different threads and the timing works out just right, you might end up losing a node, or you might end up making a loop that points back to itself, or all kinds of things, right? So when it says that these things are not synchronized or they're not thread safe, that's what it's talking about. If you're going to have a possibility of 2 or more threads accessing this, you need to synchronize it yourself, right? And we talked about the synchronized keyword with the voting machine, so this is a case where you would use it. Now, some of these things are synchronized, but generally they're not. When we talk about hashes, there's hash tables and hash maps. Hash tables are synchronized for you. Hash maps are not. So you got to check the documentation if you're going to hit these things. And if you do that wrong, again, it's one of those things where everything works great, except every like 15 minutes or so I get a null pointer exception, right? And if you see something like that, and you got threads, start thinking thread safety. It's probably something where you have 2 things accessing something in an uncontrolled way. Okay, then there's Treemaps. So Treemaps are nice because they will sort for you. Map is sorted according to the natural ordering of its keys or by a comparator provided at the creation time. So this is what's called a red-black tree. We're going to talk about red-black trees next week or the week after. This is a way to keep trees balanced. Generally, we do AVL trees or red-black trees. And it's a way to insert and remove from a tree, but keep the balance pretty close to perfect. So this uses red-black trees. Don't need to know that to use it, okay? And it's generic, so you have to specify what type of data you're going to store in it. You construct it as just a tree map, but you can also give it your own comparator if you want. Because we don't have to use straight integer comparison, right? Or we don't have to use alphabetical comparison for strings. We might have some other notion of what it means to be greater than or less than. And the only thing it changes in your code is what operation you do when you're traversing your tree and trying to decide whether to go left or right. Right? So it fits nicely into a generic model. Just specify what kind of comparator you have. And so all the usual stuff that we have with lists. So you can add, you can find the first key, you can get, you can find the size and remove entries and put and so on and so forth.
What was the other type of tree you said other than red line?
AVL. Not KCL. That would be cruel. How are we doing on time? Oh, we got a few minutes. Yeah, let's play with a tree map. So this is going to be like a hash, right? That's the map part. It's going to be a key value pair. What did I do? I missed the uppercase. All right. So I don't need my list iterators anymore, but I might. So we'll make a tree map, and Treemaps, right, so you put with a key and a value, okay, so like a hash table, and you can get just by using a key. and it'll return whatever value is associated with that. But the tree part is that it alphabetizes these for you. So let's do something like this, tm put
By key or?
by key.
So alphabetizes your name, not the.
Yeah, it should be off of key. Alright, so I switched to art. So we'll store 4 pieces of information keyed off of names, and first I'm storing Nick with CS, and I'm switching it to Nick stored with art, right? So this is a hash. The first value is the key that we're using to index the second piece of information. So if we ask for the information associated with Nick, it should come back with art. For example, so let's pull this out in sorted order. So there's a first key method that will get us back to, will get us the key of the first item, right? I know someone who's rewatching 4400, so first key is tripping my brain a little bit. So, well, this is not null. So, and then we'll just do the get method on the key. So this is a different version of an iterator, right? So Treemaps have this get first key method, or this first key method returns the lowest key currently in this map, so the first one alphabetically, and then we can say higher key, and we can give it a key, and it'll give us the key that comes right after that. So here we want to say key equals tm dot higher key. So we give it the key we just had, and it'll give us the key that comes after that. And we can just iterate on that. So we got Nick, Izad, Carol, Tina, and Nick. And if we run this, we get our data out, and it's alphabetized by the key, not by the data. So this makes Pt2 really, really short, right? Because basically for each word, the data you would store is just a linked list of integers. And when you get a word, you check to see if it's in your tree map. If it is, then you just go ahead and call the add method on the linked list associated with that data, and you say add this number. If it's not in there, then you just go ahead and add the key value pair with a linked list containing one entry, which is the position of that, and you're done.
So tree map of linked lists.
So a tree map of linked lists of integers should do it. Well, yes, so your key is just your word, and your data is a linked list of integers.
And then you said that stores alphabetically.
Mm-hmm.
Because you said string, if you would have said integer, is it numerically?
It'll do it numerically, yeah, it's a default comparison. But again, you can specify your own comparator if you want to sort by how many factors or the sum of its factors or something like that. All right, so let's play around with hash tables and hash maps on Monday, just for completeness. And then maybe we'll start talking about trees, and we'll finally talk about balancing trees. So we'll do AVL. No, balancing trees is fun, man. You're gonna like it. And then I believe your midterm is on Wednesday. Is that correct?
Yep.
So maybe Monday we'll talk about the midterm. as
You guys
well.
canvas?
Well, yeah, 'cause I don't look at Canvas, you know.
We don't use ours, so.
Yeah, yeah.
Yeah, we have to